Perfect. So yeah, first of all, hello everyone, and thank you the organizers for giving me the opportunity to tell you about our work in this great seminar series, Quantum Myths. So I'm Jose Carrasco. I'm a postdoc in the group of Jens Seissert in the Free University Berlin, and I will tell you about our recent work together with Marcel and Jens himself. Marcel is a PhD student here on the state hidden subgroup problem, more precisely the abelian version of the state hidden subgroup problem. You can find this manuscript in archive, but it has been recently accepted in PRX Quantum, and it was also presented and accepted on some major conferences. Okay, so let's start. I will give you a brief outline of my talk. Sorry, maybe I ask a question. Can you see my my mouse? No.
We cannot see your mouse, no, unfortunately.
Okay.
That sucks.
Yes. Okay. Okay, I think we should be able to still do it. Okay. Okay, so this is the outline of my talk. So more or less, I would try to tell you about these 5 things. So first of all, of course, what we have to do is to make it clear what is this state hidden subgroup problem, right? And I think that a good strategy to this end is to start with the standard hidden subgroup problem that most people know, and then compare it to this state hidden subgroup problem that is in a sort of, in some sense, its quantum version, right? Then second, what I would like to also tell you is about some previous work on this topic, essentially on entanglement location. Entanglement location, we will define it as a state hidden subgroup problem, purely quantum, that cannot be cast in the form of a hidden subgroup problem. And also in this case, the group is abelian. And in this previous work, they show how to solve efficiently with a quantum computer this state hidden subgroup problem entanglement location. Then essentially, what we do in our work can be seen as an improvement over this non-quantum efficient solution, in a sense that we can solve this problem quantumly in a way easier manner, in the sense that we get rid of some ancilla qubits that they have. We also get rid of some coherent measurements over several copies. Our protocol is single copy, and also we don't need some heavy unitaries like the control action of the group. This will be more clear later, but just to let you know in which sense, what is the context of our work. It's just an improvement over a previous solution. Then after that, another thing that was interesting from our work is that we also show that some learning tasks in the literature, like stabilizer learning, can be cast actually into they are essentially instances of a state hidden subgroup problem. This wasn't known because so far as I know, only this entanglement location was known to be a state hidden subgroup problem. But here we show that several other learning tasks, like stabilizer learning, and also instances of state hidden subgroup problem. And also finally, we introduce a totally new problem that we call this locating translation. And we also show that it's an instance of abelian state hidden subgroup problem. Therefore, it can be solved in this form. So, and then I will finish with some open questions and outlook. Okay, so let's start with a quick recap of what is the standard hidden subgroup problem. I don't know, I haven't said it, but for sure you can ask questions anytime. I cannot see you, so yeah, you have to speak. Okay, quick recap of the standard hidden subgroup problem. First of all, the standard hidden subgroup problem has a purely classical formulation, right? So there is a group G and a hidden subgroup H, and the goal is to identify this hidden subgroup H. No, then the question is, how is this subgroup hidden? In which sense is hidden? Well, it's hidden in the sense that what we have is access to a function f that maps elements of the group into some set X. This doesn't matter much. What is important is that this function evaluated in two group members, G1 and G2, is equal if and only if these two guys, G2 and G1, are related by some element H of the subgroup. Here I write plus for the group operation because we will mostly be interested in abelian groups, but this can also be defined for non-abelian groups. Then any non-quantum approach to try to identify H, just having access to the evaluations of the function f, whatever he does can always be phrased in this form. So you take q elements of the group, right? G1, G2, GQ. You evaluate f on them, so you obtain f of G1, f of G2, and then you apply any algorithm and you try to recover H, right? So then here the idea is that if you see, for instance, that f of G1 is equal to f of G2, then you know that the difference G2 minus G1 is in H, right? And if you see that f of G1 is different from f of G2, then you know nothing. You have learned nothing. Well, the question is how many times Q you need to call this function f. Well, what it is the case is that for all non-quantum algorithms, this Q grows exponentially with the logarithm of G, that is the size of the input. However, there is a quantum solution for this problem that is efficient. So this is what I want to tell you here. So this is just as before. This is the definition of the problem, is the same as before. But the difference here is that with a quantum computer, if you have access to f, you also have access to this unitary UF that implements the function, but in a qubit register. So therefore, you can actually compute this function in superposition. So this, together with the Fourier transform, actually allows you to solve this problem efficiently. So what you have to do is something like what I sketch here. You prepare something like a superposition over all group elements. Then you apply this UF in superposition. You obtain this state in the middle, that is a superposition of all group elements G together with f of G in the second register. And then it follows that by applying quantum Fourier transform, or its inverse actually, and measuring and post-processing, you can actually identify H. And all these circuits here are polynomial in the logarithm of the size of the group, that, as we have said, is the size of the input, because of the number of bits that you need to identify group elements, and the number of measurements required are also polynomial. So then what we have seen is that standard hidden subgroup problem, as we all know, is a classical problem that has no known efficient classical solution, but has an efficient quantum solution. Now let's move to state hidden subgroup problem, StateHSP. That is similar, but a bit different. So first of all, state hidden subgroup problem is intrinsically quantum, even in its formulation. For sure, there is still a group G and a hidden subgroup H, and the goal is to identify this subgroup H. But the difference is how is this subgroup H hidden, right? So in the StateHSP, the subgroup H is hidden by providing a quantum state psi that is invariant under the action of the subgroup. More precisely, in more formal terms, this is what you have. This is the promise. So there is a representation R that maps group elements to operators in a Hilbert space, such that for all elements of the subgroup H, then the state remains invariant under the corresponding action of RH. And for all elements G that are not in H, what you can see is that the action of Rj on psi somehow is at least epsilon far from being invariant, right? This is what condition 2 means. When you act with Rj on psi, what you get is at least epsilon away from psi. So this is state hidden subgroup problem. And now I want to make 2 remarks. The first one is that all hidden subgroup problems are state hidden subgroup problems. because this UF that appears in the hidden subgroup problem allows you to prepare this so-called coset or invariant states. Actually, what you can also think is that HSP is state HSP when epsilon is equal to 1. Because when you try to solve quantumly this hidden subgroup problem, and you prepare these invariant states that I have written there, they turn out to satisfy these 2 points, 1 and 2 on the left, for epsilon equal to 1. So they are not only invariant, but they are also such that when you act on them with an RG, where G is not in the subgroup, what you get is something that is completely orthogonal. Then the second remark that yeah.
Before you go on to the second, I have a very silly question, right? So here it looks like you have a sorry. It looks like you have a notion of robustness, right, built in the second condition, because you're saying that, you know, like you're adding some epsilon there, right? You're saying that after you apply RG, you want it to be far away from the initial state somehow. Is there a sense in which one can think about the first condition also being a bit more robust? Like maybe there is some delta and they're somehow close. Does that make sense, or is it?
That's an excellent question, and actually, the more one thing that makes all the sense is to have here 2 parameters, epsilon 1 and epsilon 2, and you would say that condition 1 provides a state where the overlap is larger than 1 minus epsilon 1, and condition 2 is overlap smaller than 1 minus epsilon 2, right? For sure, you need that epsilon 1 to be smaller than epsilon 2, right? This is an excellent question, and it turns out that it's not clear for which type of problems the such version, that let's call it the noisy version, can be also solved or not. And also it's not clear when one can show that it's hard. We will discuss this a bit later, but for instance, with these methods, it turns out that at some point you have to do some Gaussian elimination. We will see this clearly later, and therefore what you can do is reduce the noisy version of the problem to learning parity with noise. So if learning parity with noise is hard, you cannot solve the noisy version of the problem, at least for this entanglement location. But there are other cases, for instance, stabilizer learning, when we can show that it's robust to this noisy version. So actually, it's an excellent question. So it turns out that there is not a general answer to whether or not such a noisy version can still be efficiently solved.
I see. Thank you so much.
Yeah, you're welcome. Okay, and then the second remark that we want to make here is that we see this within the framework of learning theory, right, or quantum learning theory. That is essentially, given IID copies of an unknown state, you want to learn some aspect of it or make some predictions. I stress this because also a novel part of our work is to show that other known problems in learning theory, like learning stabilizers for qubits or qudits, can also be cast as state-hidden subgroup problems. And in particular, we show that routines like Bell sampling or Bell difference sampling are just Fourier sampling in the when you frame them in the right language. So yeah, so this is the second remark that I want to make here, that some known learning problems are actually instances of state-hidden subgroup problem. Okay, so I hope that now it's clear what state-hidden subgroup problem is. And I think that next what I want to do is to discuss in a bit more detail this entanglement location example that I think is a nice one. So let's go step by step. So suppose that you have a state phi that is a product state across some bipartition C, right? So it's a product of phi1 times phi2, where phi1 is supported in C and phi2 is supported in C prime. You are just promised that there is such a bipartition, but you don't know the bipartition. For instance, in this example, it turns out that this bipartition C contains the qubits 3, 4, 6, and 7, and its complement, right, is the rest of the qubits, right? for sure, instead of this C, I can also label this C by a bit string of length n, this S, that has ones in the positions where the elements. So sorry, the if entry of S is 1 if and only if I is a member of C, right? So the goal is somehow from copies of phi to identify this cut across which the state is product. So this is, we have to find a bit string S, and there are 2 raised to n possibilities, right? Because it could also be that the state is product across this other bipartition. This is a different one, or across this other one. So there are too many of them to be checked, right? Nonetheless, this problem is officially solved, right? So you don't need to check all bipartitions. So you can actually output the right one. And this is because it can be cast in the form of this state hidden subgroup problem. Maybe something that I can say here is the following. Consider this example a bit smaller for 5 qubits, where the qubits 1, 2, and 5 are entangled, but and the qubits 3 and 4 are also entangled, but they are product among them. No, so it's what is pictured here. And now consider the state psi that you made out of 2 copies of this phi, right? So I hope that you can bear with my diagrams what I mean by these blue and red parts and what I mean by the 2 copies, right? Now consider these swap operators Si that swap the eth qubit of each copy, right? For instance, let's see an example. Here, what I have is S1 acting on psi, no? So S1 means that I swap the first qubit of each copy. So what I have is something like this diagram that I have written here, and you can see that this is different from psi, right? Diagrammatically even. But this is because you are swapping a subsystem that is entangled, right? But you could also convince yourself that if you, for instance, take psi and swap the qubits 2nd and 5th position, then you are doing nothing, right? Because you are just swapping all the qubits that are in blue. Also, if you just swap the qubits in the 3rd and 4th position, also you do nothing because you are just swapping the qubits that are red. And for sure, if you swap all the qubits, you are also not doing nothing. So somehow you can convince you that there are some sets of swaps that leave the state invariant. Precisely the swaps that leave the state invariant are those that are, say, supported on the bipartition that you want to find. So this is precisely what you need for this state hidden subgroup problem, right? So in particular, what you can do is to define a group and a representation. You can take as the group set 2n with addition modulo 2. So the elements of the group as are bit strings of length n, and then you can define this representation, right? Where given a string g, g1, g2, gn, what you construct is this operator that swaps the corresponding subsystem where the g1s are 1, right? So in this particular example that we have here above, the subgroup H would be the subgroup containing these 4 possible elements, right? Because what you can do is to swap the qubits 1, 2, and 5. This is the first element of H. The qubits 3 and 4. This is the second element of H. All the qubits or none of the qubits, right? So this is actually this is an abelian group, right, generated by these 2 elements. Then there is this epsilon parameter in the state hidden subgroup problem that I hope that will be clear a bit later. But for the moment, let me just say here that it will determine the number of measurements that we need, and it will depend on the entanglement of phi 1 and phi 2. So on the entanglement of the states within each subsystem. Okay, so now, as I said at the beginning of in my outline, so there was already someone else in the literature studying this problem, and this is this famous work of Boland and collaborators, where they showed that The entanglement location can be phrased and solved as an instance of abelian state-hidden subgroup problem. And their solution is a bit like as follows. So what they need to do is to take the state psi that is invariant under the action of these swaps. Then they prepare additional axiatic qubits where they prepare uniform superposition over group elements. Then they need to apply this UG that I will call it like the control group action, where this is an unitary that depending on the state of the first register, if it is G, apply RG on the second, right? So this is this control group action, UG. Then they have the state that you have here in the middle, this superposition. Then they need to apply this group Fourier transform, right? So because this is the like quantum Fourier transform where the coefficients are given by the characters of the representation. We will talk more about it later. And then they measure and then they identify H. And all this is efficient. So they show this in this paper. Then one part of our work can be seen as follows. And it's like this entanglement location particularly can be solved by just measuring a simple POVM in single copies of psi, because this is something that I haven't said here, but they also need several copies of psi. This will also be clearer later. But the important thing is that we don't need the action of this control group unitary, this UG in the middle, nor also quantum Fourier transform. Actually, we just need to measure unknown CJs. We just need to measure psi in the Bell basis. And then when we realized this, we saw that actually there are other learning problems that can also be solved in this form without CJs or without the quantum Fourier transform, without the control group action. And in a simple manner, and we also introduced some new problems. So as a summary, our work, this is the main picture. Yeah.
So before you go on, so I have a question about the Bell basis measurement. To perform such non-local measurements, I suppose you do need some processing, right? Like suppose you only have access to standard basis measurements, then to be able to measure in the Bell basis, do you need ancillas to be able to implement it? Is that
no?
I see.
Exactly. This is what in our work, this is what we discuss. So you don't need any ancillas because you just need to measure in the Bell basis. You just need to apply C0 and then Hadamard, right? So that's it.
Okay, so it's not like a generalized Bell basis. It's like, okay, really the Bell basis. Okay, got it.
Yeah. Exactly.
I just wanted a clarification. So this entanglement localization becomes a state hidden subgroup problem if we have two copies of the state, right? Like so that the swap becomes the hidden state. Like, can it be solved with just a single copy? Like, is this what you're saying in the last slide?
No, I don't think so, because what you would need to find is just a group G with an action such that there is a subgroup that leaves this phi invariant. And this I don't know. So and I don't know if even such a thing exists. But however, if you consider this psi that is 2 copies of phi, then indeed you see there is some action of a group that leaves this state invariant when acting on the right positions, right?
Yeah.
So somehow, for sure, you can solve it with single copy measurements, but single copies on the state psi that defines the state hidden subgroup problem. It just turns out that the state psi that defines the state hidden subgroup problem is made out of 2 copies of a state with this product structure.
Right. So like we need 2 copies of like a single copy of psi, but like that is made up of 2 copies of phi. Right?
Correct.
Okay.
Okay. So we were here that this is somehow the main figure of our work, and we try to summarize our findings that are, as I just said, you can see them as a building upon this previous work and as a refinement and introducing new examples. So essentially what we do is that to solve a state in a subgroup problem for abelian groups, you just need to measure this character POVM on single copies. So you don't need coherent measurements. And for these known examples, this can be done very easily with low depth circuits, even with constant depth circuits like this Bell sampling or Bell difference sampling. So we find that that some known learning problems can be cast into this form, like learning qubit and qudit stabilizers, and also these new translational symmetries that we introduced, right? So this is a bit of a summary. So let me tell you now a bit of the details of why our approach works. And for this, I just need to tell you very little things about representation theory. So once you have a representation of a finite abelian group, let's start with that. For sure, for any representation, you can decompose the linear space where the representation acts as a direct sum of irreducible representations labeled by lambda with the corresponding multiplicity. Then there is this dual group of characters. So it turns out that once you have a group, there is the dual group that is constructed from the characters associated to the reducible representations. And for finite abelian groups, this dual group has the same cardinality than the original group. So this is because for abelian groups, the number of irreducible representations is equal to the number of elements of G. So therefore, what all this means is that you can find this basis, this basis lambda, new lambda, where lambda labels irreducible representations, and this new lambda just goes from 1, 2 up to the multiplicity of that irreducible representation. And then you have this for each irreducible representation lambda, you have these projectors, right? When you just this pi lambda is just summing over all possible basis states with label lambda. So you just sum over all these nus, and this can be seen from basic representation theory that this projector can be written in this form, with this chi lambda is the character associated to reducible representation lambda, right? So here the first equality is just the definition of this projector lambda, right? So I'm just summing over all basis states where that span the reducible representation lambda. And the second equality is what is a bit less trivial, that this is equal to summing over all operators RG weighted by the conjugate of these characters. But this can be seen from the basic representation theory books. But then what you can also realize is that this is also well known that for every subgroup H of G, there is a unique H perp, as we write, and a unique subgroup of the dual. So you can define this H perp, also called the annihilator of H, by the set of lambdas such that the character evaluated in H is equal to 1 for all H in the subgroup H, right? So this is somehow a bit like in vector spaces, right? Once you have an inner product, given a subspace, you can define its orthogonal complement, right? Spanned by all the vectors whose inner product with respect to the guys in the subspace is equal to 0. This is a bit similar, but it turns out that that finite abelian groups, even though you don't have an inner product, you can also define some sort of notion of orthogonal complement. More precisely, what you can do is to define this annihilator, that is a subgroup in the dual subgroup. So this is the proper way of doing it. And you can see that H uniquely identifies H pair and vice versa. Okay, so then another thing that I want to, we can stop a bit after I say a couple more things, because I think this is important. Then, since we are considering finite abelian groups, these operators RG, they commute, right? So they, because the R is a homomorphism of groups and the G's are abelian, so these operators R commute. So therefore, there is a common eigenbasis. And the common eigenbasis is precisely this basis lambda, a new lambda that we have introduced before. So in other words, an irreducible representation, lambda, just tells you is a vector that is a common eigenstate of all RG. And actually the eigenvalue is given by the character. So this is what I have written in the line below. So it follows that these lambda states are eigenstates of RG with eigenvalue chi lambda, the character evaluated, and G. Or in other words, you can also see that these operators R of G can be written as a sum of projectors into irreducible representations lambda weighted by these characters. This last equation, RG equal to this sum over irreducible representation, is just the inverse of this previous equation of this one, right? Last equation of this slide. If pi lambda is equal to a sum over all RG weighted by the conjugate of chi lambda, by the orthogonality of the characters, you can invert this equation and write RG as here in terms of the projectors pi lambda. Then last thing here, I know that it's a bit more technical, but I think we have time and it's interesting. Then if you have a state phi that is invariant under the action of RH for all H in a subgroup H, then it turns out that the support of this distribution Q is precisely H perp. So maybe let's take a bit of time to digest this last line. This is also non-trivial, but you can see it in the paper that this is the case. So what I'm saying here is the following. So you have a state phi, right? Since the state phi, since this a common eigenbasis lambda, nu lambda, is indeed a basis, this state phi can be imagine that you write that the state phi in that basis. Then for sure there are some coefficients that define this q phi of lambda, where it's just the expectation value of this projector, right? So this is a probability distribution because these projectors sum up to 1. Then what I'm saying here is that if you sum the values of this q phi of lambda for all lambdas in H perp, this is equal to 1. So this distribution that actually we will call it the Fourier distribution of phi is just supported on H perp when phi is invariant under the action of elements in H. I hope that this is clear, at least what I say. But yeah, you can find more details in the paper. Okay, so then I will go a bit further, and let's discuss the algorithm that we proposed in the paper. So you start with this state psi.
Sorry. Could you say again why that is the case, that the support of phi is only on H perp?
Yeah, this is unfortunately it's not. I cannot explain here, so it's a bit technical, but it just follows from the first. It follows from the first property of the state phi. So the idea here is that well, you can see that. Wait a moment. Right. So what you have to do is to use the fact that for all lambda in H perp, right? You have that the character exactly R1 for all G's in G, right? And then you have to use this formula. Sorry, before. Here you have to use this this formula. The fact that the projector into lambda can be written in this form, right? And then you can see that when you sum over lambdas in H perp, only the G's in H will remain. And then you just use that the cardinality of H times the cardinality of H perp is equal to G, and you get this result. But yeah, this follows from the first property. Yeah.
I see.
It's not so complicated. It's just a bit technical. What you have to use is the orthogonality of the characters. Yeah.
Okay. Thank you.
Yeah, you're welcome. Then, okay, so let's discuss a bit more in detail this algorithm. So what we start with the state psi, that is the promised state of the state hidden subgroup problem. And then what we do is to measure in this common eigenbasis of these Rj's, right? M times, and you will obtain some lambdas, lambda 1, lambda m, that are IIT distributed according to this cube psi, right? This is what we have said, and this can be called Fourier sampling. And this can be done for a single copy by just measuring the common eigenbasis. Then what you would output is this H prime. That would be what you have to do is to compute the orthogonal complement of the subspace generated by these lambdas, right? The kernel of the span of these lambdas. And this can be done via Gaussian elimination. We can see it in more details with an example in a moment.
So before you go on, can I quickly ask another small question? So
sure.
You measure in the common eigenbasis. I guess it's the one that you explained in the previous section, right?
Correct.
So is that also efficient to compute? Like, given a group, can you easily compute the common eigenbasis? Is that obvious?
That is also an excellent question, and I think that in general it's not. Yeah, exactly. But what we do in the paper is to show that for all known instances of state hidden subgroup problem, actually this common eigenbasis can be easily identified. For this entanglement location is just the Bell basis, that is just depth 2 circuit. For learning stabilizers is this Bell difference sampling, that is essentially twice the Bell basis. For qudits is also constant depth, so even for qudits where d is larger than 2. And then for this locating of translations, we also explain, well, I can explain you in this talk. In the paper, we didn't give much details, but also in that case, we can explicitly construct this eigenbasis. But again, this is a very well, an excellent question. That's the point. Yeah.
Right. Okay. Thank you. That's helpful.
You're welcome. Okay, so we are here. So yeah, as you said, so we measure in this common eigenbasis we get these lambdas. Then we compute the orthogonal complement of the span of those lambdas, right? And this can be done via Gaussian elimination. And then what about this epsilon of the definition, right? Well, recall the promise, no, that I have written here again. So then this epsilon enters as follows. First of all, you can see that this H prime that you construct in this form will always be larger than H, that the subgroup that we are searching for. This is because the lambdas that we observe are always a subgroup of the H perp, or the true H perp, and therefore the H prime is larger than H. So by construction, this H prime that we output is larger than H. Therefore, the probability that this H prime that we output is different from the true H that we are looking for is the probability that this that the true H is a strict subset of H prime. And then we can upper bound this probability to be exponentially small in delta if we take this M to be of this form, logarithm of the cardinality of the group divided by delta divided by epsilon square, where this epsilon square is the epsilon of the definition. And I can tell you now a bit the intuition why this works this way. I think that would also be worth it. So the idea is that once we measure in this common eigenbasis of all the RGs, then this thing that is the average of the observed characters evaluated at G, this is an unbiased estimator for the expectation value of RG, right? Because by construction, these lambdas are the common eigenstates, and the eigenvalue is precisely the character evaluated at G. So therefore, this quantity is an unbiased estimator of this expectation value. Then, if you, by Hofstad's inequality and similar, and the union bound, what you can see is that the probability that there exists one G such that this estimator is epsilon away is for sure smaller than the number of elements of the group, so cardinality of G, times exponential of minus m times epsilon square, right? So the first factor G is just the union bound, and the second factor is just Hofstad's inequality, because these characters are bounded. And actually here you can see, this is just the intuition, right? For the formal proof, please go to the paper, but this is, I think, a way to convince yourself how the epsilon enters. Then here you can see that taking m of the form that I said before, you can make this probability really small. So if you take m of that form, you can be certain that with probability at least 1 minus exponential of minus delta, all the RGs are estimated within error epsilon, right? From the m lambdas that you have observed. Therefore, once you have that, if the H prime that you output is different from H, as we have seen, this means that H is a proper subset of H prime, then this means that there is an element in H prime that is not in H, right? So this is what I wrote here. So there is a J that is not in H such that this estimator is 1, because this is the definition of the of H prime, right? But if J is not in H, but the estimator is 1, it means that the estimator is large, the difference between the estimator and the true value is larger than epsilon, right? And we have seen before that this happens with probability at most exponential of minus, sorry, here there is a typo, at most exponential of minus delta. Okay, so now I want to make a kind of summary of our message. So what we say in our paper is like, okay, if you have a finite abelian group G and this promise, then what we suggest to do, and if you can compute the common eigenbasis, excellent question, then what you should do is to do m single copy measurements in the common eigenbasis. Then with this, you will sample characters lambda according to this cube psi, and this distribution is supported on H-perp, but need not be uniform. This is important. So then what we say is that for any such cube psi that is supported on H-perp, then this promise, the problem implies that the span of these m lambdas that we have seen can be written in terms of some independent generators, and then when m is equal to the logarithm of the cardinality of the group divided by epsilon squared, by linearity of the characters, we can recover H from H pair by Gaussian elimination. Now here, I think an important technical contribution of our work is that it is clear that when this Q, when the Fourier sampling is uniform over H perp, it is clear that to uniquely identify H perp, you need a number of measurements that is proportional to the logarithm of the cardinality of the group. This can also be seen by the fact that when this distribution is uniform over H perp, this corresponds to the case when epsilon is equal to 1. But when epsilon is not equal to 1, this distribution Q need not be uniform over H perp. So then it's not clear how many samples from Q you need to completely characterize H perp if Q is not uniform over H perp. So then previous approaches, like this paper of Buland, what they do is also informally, please, but more or less their idea is that to use the control unitary, this UG, coherently on T copies of psi, and then what you would be doing is somehow amplifying this property is 1 and 2, right? Because if you have T copies of a state psi, then the second inner product, sorry, the second expectation value that in the second property would become 1 minus epsilon raised to T, right? And then choosing T like proportional to 1 over epsilon, this condition 2 can be really made really small. So you would be back in this situation where this distribution Q is actually uniform. So this is the way they solve it. And what we do in our paper is to prove that there is no need for that. Just with order log G divided by epsilon squared samples from Q, one already can recover H. And in addition, since we just need to act in a single copy, then to measure from this cube psi is really to measure in the common eigenbasis that in most cases can be identified. So I think this is a nice summary of our work. And what I would do next.
The sample complexity only depends on group size, or does it ever depend on size of Hilbert space? Or if that's a silly question.
No, exactly. No, it's exactly like this. Yeah, so it doesn't depend on the size of the Hilbert space. That's correct. I mean, for sure, what will happen is that usually, well, no, but yeah, this is exactly that. For instance, I think that this is a nice thing that we will see in the example now, because, for instance, for this entanglement location, right, there you have n qubits, right? But the group has cardinality 2 raised to n. So there, for sure, the logarithm of the cardinality of the group coincides with the number of qubits. But in principle, if you can find...
so is there ever a case where the algorithm's complexity scales with log G, but the state maybe lives in a larger Hilbert space? So if that's the case, then so your algorithm would work, but implementing the measurements would require resources that exponentially scale with the number of qubits?
Yeah.
Is that ever?
Yeah, that's totally correct. That wouldn't be an interesting case. For sure, that is not the case in this stabilizer learning of entanglement location. And yeah, I think one interesting line of research that we have is to find new instances of state hidden subgroup problem, right? So this means to find concrete representations on systems of qubits. For sure, if such a new instance of a state hidden subgroup problem is, as you say, that wouldn't be an interesting one, for sure, yeah. But the ones that we construct are not of that form. Okay, so I guess that's we are fine with that. So then let's come back for a moment to this entanglement location problem, right? So these slides, and this group, there is this H, there is the epsilon, and here, as we have said, is that we need to measure in the common eigenbasis of this Rj, right? So the common eigenbasis is the Bell basis, right? So what you have to do is prepare 2 copies and measure in the Bell basis. This is to apply this unitary U dagger that maps, say, the computational basis into the Bell basis. And we have said that this identifies an irreducible representation lambda. Let me just tell you what this lambda is. Well, this lambda is just an n-bit strings where lambda I is equal to 1 if and only if the corresponding Bell state is a singlet. So this is why I write lambda I equal to bi times b prime I, because this is 1 if and only if the corresponding Bell state is the phi 1, 1, right? That is the antisymmetric one, right? So then what you have to do is to measure in the Bell basis, and you put a 1 if you see a singlet. And if you see any of the other symmetric state, if you see phi 0, 0, phi 0, 1, or phi 1, 0, you put a 0. And if you see phi 1, 1, you put a 1. And that's your lambda. Then you can see that the multiplicities are like this, but this is not so important at the moment. So then the point is that these states are eigenstates of these swap operators, right? And the eigenvalue can be written as -1 raised to g times lambda, right? Where again, lambda is just a bit string with a 1 whenever you see a singlet. Then if you want to compute the eigenvalue corresponding to Rg, this is just -1 raised to g times lambda. Then what you need to do is once you have observed m lambdas, what you need to find is an S such that the product with respect to with each of the lambdas is equal to 0 modulo 2, right? So what you need to find is the kernel of this matrix capital lambda that you can write in this form. And this can be done by Gaussian elimination, right? Here you can see this robustness thing, at least with this method, if so the point here is that if your state is not exactly invariant under the action of the subgroup, but only 1 minus epsilon 1 invariant, then with large probability, you will find that the kernel of this matrix is empty. Nonetheless, there will be an S such that is equal to 0 most of the times, but not for all lambdas. It will be for a large fraction of the lambdas, there will be an S such that the inner product is 0, but most likely not for all lambdas. So in that case, this will be equivalent to this learning parity with noise that is known to be hard. But maybe there are other methods by which you can solve this problem. So that's an important comment that I wanted to make here. And then another example that we have in the paper is stabilizer learning, where the common eigenbasis is essentially this Bell difference sampling that is essentially 2 copies of Bell sampling. We also show that you can do similar things for qudits, where this wasn't known before, because here the point is that for qudits, you need to measure d copies of a state. And before it wasn't known that how to post-process the so-called Bell states for qudits, even though there are important works by Alcock and collaborators where they discuss this Bell sampling for qudits. I recommend these papers. They are really nice, where they somehow show that there's still these Bell states on 2 copies of qudits, they are still useful for certain tasks. Okay, so then let me start a bit wrapping up. So one of the main applications or motivations of this type of our work and others, this state in a subgroup problem can be seen as more efficient tomography methods, right? Like for certain classes of states, for instance. It is if you know that the state you are trying to do tomography is a stabilizer state, then for sure you apply certain methods. But if you know that the state you want to do tomography on is, say, low entangled, then you would try MPS tomography, right? So this type of thing. So therefore, what one can think is that identifying the symmetries of a state can be seen as a previous step before deciding which sort of method for restrict tomography one should use. So this is a way of thinking about the uselessness of state hidden subgroup problem. Then another motivation and application is a bit more abstract, but I like it a lot, and this was already present in the work by Boland, that is the cost of pseudo-random states. So let me say a bit about this. So suppose that this is state phi, right? Let us talk here about the rank R of a state phi across bipartition C, right? So this means that that the state phi can be written as a sum, right, or a superposition of at most R product states of this form, right? By this I mean that the state phi has rank R across bipartition C, right? And assume that this phi is at least epsilon far from any state of rank R minus 1. Let's more or less have this definition in mind. Then what we have seen, right, is that rank 1 cut can be located efficiently, right? This is disentanglement location. I can phrase it as the fact that rank 1 cut, if you are given a state such that there is a cut for which the state is rank 1, this cut can be located efficiently, right? We have seen this. Then, interestingly, there is this gluing theorem for random unitaries that essentially tells you that you can prepare a pseudo-random unitary by smaller pseudo-random unitaries that just overlap in omega log n qubits. So this immediately implies that that rank omega log n cuts must be hard to locate by any method, no matter the method. Then I have also more or less indicated, but this you can prove it more efficiently, that rank 2 cuts cannot be located efficiently via this method if LPN is hard. So therefore, I think a very interesting open problem is to show that locating rank 2 cuts is hard by any method, right? So far one can only think that via this Gaussian elimination, yeah, it should be hard, but maybe just using the hardness or the existence of hard random states and techniques like that, one can show that locating rank 2 cuts should also be hard in general, as it is, for instance, as soon as.
So yeah. Just to be sure that I'm understanding, so we don't have like a formal proof, right, that says that identifying rank, like we don't have a reduction, right, that says that if you can solve rank 2 cuts, then you can solve LPN. We are just saying that if we follow this specific procedure, then it appears that you would need a solver for LPN, right? It's not like a formal reduction, is it?
Yes, yes. Please take this. Thank you for the question. Please take it like that. So this is using this concrete method here, correct?
Right. Okay. And this LPN is learning parity with noise.
Yes. But I don't know. I think it might be quite possible that that maybe one can prove that this problem is hard by any method, you know?
Right.
I think that would be an interesting thing, yeah.
Right. Okay, thank you.
Yeah, you're welcome. Okay, so then as I told you, there is also this locating translation problem that we introduced that wasn't there previously in the literature, where you can consider the cyclic group of n elements, and then you can consider a representation just defined by but n unitary on n qubits such that t raised to n is equal to 1, right? So for instance, one can consider this particular case where you just shift the qubits, you bring the Bn to the first position, and then you add just a phase factor, and this phase factor is defined in this form such that the nth power of t is equal to the identity. We choose this phase factor in this weird form because actually what we want is that this t is a sequence of these so-called fermionic swap operators. That is just the same as a standard swap, but adding a -1 whenever the two inputs are equal to 1. Because in this form, what you can see is that the unitary that diagonal the unitary that maps the standard basis into the common eigenbasis of this t is the so-called fast fermionic Fourier transform that can be implemented efficiently. So this is answering actually the previous question. So if you just give me an arbitrary t without this phase in front, it might be that the unitary that maps the computational basis into the common eigenbasis cannot be implemented efficiently. But if you put this phase factor in front, then it turns out, therefore, this means that this t can be written as a sequence of fermionic swaps. Then we can write down the unitary that diagonalizes this transformation in an easy way, and it's known in the literature. But yes, I will not give you the details with that. Maybe if there is some question, we can go through it, but I will already leave you with my summary. So a couple of things that we do in our work, first of all, is that realizing that the state-hidden subgroup problem is an essentially learning task, and that some known learning problems can be cast into the form of the state-hidden subgroup problem. Also that the abelian state-hidden subgroup problem can be efficiently solved just via Fourier sampling without ancillas and without control unitaries, just measuring the common eigenbasis that can be found easily for known examples. And this allows us to just, for instance, solve the hidden cut problem just via Bell sampling or stabilizer learning via Bell difference sampling, also stabilizer learning for qudit. And in addition, we consider this learning translational symmetries that wasn't considered in the literature before. And then this is the main figure of our paper that we have talked about before. So a couple of follow-up things would be really to consider the robustness. So essentially means that what if your input state is not exactly invariant, but there is this other parameter epsilon1. So then another thing that would be interesting is to find new instances of a state-hidden subgroup problem. Then another interesting problem for me is to try to investigate a bit more the unconditional or conditional hardness of the rank 2 entanglement location. And also, this is very niche, but what about this 1/epsilon² scaling? Is this optimal, or maybe one can do it in 1/epsilon steps? And we think that here, if one, for instance, has access to the preparation circuit of psi, maybe one can do some sort of Grover subroutines to reduce this scaling. Okay, so I think that I would leave it here. It was already more than an hour. So yeah, so if you, thank you very much. And if you have any questions, I'm happy to answer.